Alright, so we're going to very quickly go through our interim stations just to make sure we've got some of this information locked in for tomorrow. Alright, so I'm going to go through a few of the questions and hit a couple high points, and then the rest will be up to you to go through the stations and find the rest of the information. Alright, so looking at question number 1, it's asking basically for the energy transformation that happens when you plug in a phone and charge it. Alright? And then the phone's going to vibrate when a message comes in. So let's look at our answer choices. So A, we've got electrical energy. Well, that's true. It's plugged into the wall to charge. And we're charging the battery. We know batteries are chemical energy. Then we have the chemical energy released and used to produce light. So we see the red light. And then mechanical energy. Well, it vibrates. It's moving. So that's mechanical energy. All right. So, A sounds right, but let's check our other options just in case. B, electrical energy is converted to mechanical energy. No, batteries are chemical energy all day long. B can't be right. C, electrical energy is converted to light energy. Nope, again, batteries are chemical. D, electrical energy is converted to heat energy. Nope, so that confirms A is correct. Okay, so think about each step of the way. They plug the phone in, that's electrical. Charging a battery, chemical. She sees a light that's glowing. Well, that's light energy, radiant energy. And then the phone vibrates or moves, right? You feel it vibrating, and that's mechanical, okay? Energy of motion. Looking at number 2, okay, Marcus is teaching a lesson on energy transformation. He cracks a glow stick to show energy transformation. So construct an explanation for how the chemical energy of the glow stick compares to the light energy after he cracks it. Well, we know, thanks to the law of conservation of energy, energy cannot be created or destroyed. It can only be transformed. So whatever we start with, we have to end with. So the amount has to be the same. So A, B, and C, we're going to find the answer choice that says that they are the same, they are equal, whatever's closest to that. Okay, and it looks like answer choice A, the amount of chemical energy is equal to the amount of light energy, would be correct. 3, explain what happens to the energy in a log once it has finished burning. So again, thinking about law of conservation of energy, we can't have more in the end than we had in the beginning. We can't have more in the beginning than we had in the end. So we've got to find the answer choice that explains we have equal amounts. So A, the chemical compounds in the log are transformed into compounds that contain more energy than the original. Nope. The chemical energy in the log is transformed into radiant and thermal energy. The total energy remains the same. Yes. Okay. So now we need to look to make sure that our types of energy that it's transformed into are correct. So chemical energy in the log. We are going to get the chemical energy out. Anytime you burn something, like gasoline, wood, if you light it on fire, you are trying to get the chemical energy out of that thing. So chemical energy in the log is transformed into radiant light. Well, yes, we get light when there's a fire, and then we get heat. So B looks correct, but let's check C. The nuclear energy in the log. Nope. The only time we are going to see nuclear energy is with a nuclear power plant. That's the only form that we will see it in. So B, chemical energy in the log is transformed, and the total energy remains the same, is correct. All right, moving on to station 2, we've got heating curves. I'm going to go down to the questions here. So we're looking at this heating curve. Which statement below describes an investigation that would cause a change from points E to C? So we're looking at point E, this is a gas, to point C, there's our liquid. So we've got to describe which one of these experiments would cause a change from here to here. So Stephen places an ice cube in a hot pan on the stove and watches it as it melts into a liquid. Well, we just took a solid to a liquid, not quite. Stephen places a cup of ice water on a table and watches as the water vapor around the cup forms liquid water around the cup. Well, it's saying water vapor, that's gas, okay? So the gas around the cup is turning into a liquid around the edge of the cup. That would work because we're going from a gas to a liquid. Let's check C. Stephen pours a cup of water into a pot on a hot stove and watches As it boils, it evaporates to form water vapor. No. Okay, here's another way that we know B is correct. B is the only one where they are removing thermal energy. It's a cup of ice water, so that's cold. And because we're moving from the top part of our curve to the left, anytime we move to the left, we're removing thermal energy. We're removing thermal energy, which is kinetic energy. So our KE would be lower and our thermal would be lower. A and C, they're adding heat. We don't want to do that. We want to remove it. So it's got to be B. All right. And then let's just identify the parts of the curve that aren't here. So they've got the solid, the liquid, and the gas, the three main slopes. Okay, but what happens here in the plateau? B to C, we have freezing and melting occur. So if you see questions that say, what happens at the same time as melting? Well, your answer would be freezing, because it just depends. Are we moving to the right or moving to the left? But they both happen at this point. Then from a liquid to a gas or a gas to a liquid, we would have vaporization, which is boiling and evaporation, and condensation. So we've got to think about which direction are we going. As we go to the right, we add KE. As we go to the left, we remove KE. All right, station 3. Which method of heat transfer is shown in the thermometers above the diagram? Well, the thermometers are touching the metal plate that's here that's being heated up. So as it touches the thermometer heats up. So if it's touching, it has to be conduction. Okay, if it's touching, it's conduction. All right, Jacob is riding his bike down a tall hill. At the top of the hill, he has 2,800 joules of potential energy. At the bottom of the hill, when he is going the fastest, his KE measures at 2,650 joules. Which statement below is true? The total amount of energy at the bottom of the hill cannot equal the amount at the top. No, we know that's not true because the law of conservation of energy tells us the opposite of that. It has to be equal. The total amount of energy at the bottom of the hill cannot equal the amount at the top because some of the energy is gained. Nope. Can't destroy it, can't gain it. The total amount of energy at the bottom is equal to the amount the amount at the top, but some energy was converted into other forms due to friction. Absolutely. We've talked about that. The more KE you have, the more friction you're going to have, the more thermal energy you're going to have. So he probably lost that 150 joules to thermal energy. So C, because they have to be equal. Doesn't mean I've lost it, just means it's gone somewhere else. All right, 3. So Benny and Smalls both hit baseballs. Benny's ball travels twice as fast. How does the kinetic energy of the two balls compare? Well, Benny's baseball has 4 times the kinetic energy because it travels twice the speed. Benny's baseball has twice as much KE, or both baseballs have the same. It is A all day long, because if we remember our formula, KE equals 1/2 times mass times velocity squared. Well, because of that squared option, if we double our speed, it actually quadruples the KE. So A, it's got 4 times as much kinetic energy because it's traveling at twice the speed. 4, as the pendulum swings from position A to C, the kinetic energy increases and potential energy decreases. As the pendulum swings from C up to E, kinetic energy decreases and potential energy increases. What happens to the total energy of the pendulum as it swings from A to E? Are we going to increase our total energy, decrease it, or is it going to remain the same? And just like our previous questions, it always remains the same. So all of our KE is going to turn to PE, and all of our PE is going to turn to KE. And if for some reason our numbers aren't exact, that means I've lost some energy to, say, like thermal energy. I have displacement energy. It hasn't been destroyed, it's just found door number C and has left. Okay, it's gone somewhere else. Alright, so those are stations 1, 2, and 3. I'm going to hop over and pull up our graphic organizer for station 4 and talk about it. 1, you get a word bank here. Okay, and even if you didn't know that waves are repeating oscillations, because I know we haven't really used the word oscillations but that is an official technical term for the movement of waves. So it's just a repeating kind of up and down movement or a left and right movement. So waves are repeating. Okay, requires a medium for travel. That would be mechanical. Example would be sound. Can travel through a vacuum, EM. Example is light. The number of waves per second. How many waves do we see over that period of time? Well, there's our frequency. Waves carry energy. The length of the wave is the wavelength, and the height is the amplitude. All right, here's where we had lots of struggles. Okay, electromagnetic waves. Any wave that falls under the EM spectrum goes here. So radio waves, infrared, microwaves, X-ray, gamma, visible light, all of those go over here. The only ones that go under mechanical, sound, requires a medium, water waves, require a medium, slinky, requires a medium. Okay, so only things that require a medium would go under mechanical. So here we had to complete the statement using arrows or talking about inversely or directly. Well, as frequency goes up, wavelength goes down. So they go opposite. So if frequency goes down, then wavelength is going up. So whenever one thing goes up and the other one goes down, they go opposite of each other, we say that they are inversely related. So they're always going to do the opposite of each other. When frequency goes up, energy goes up. When frequency goes down, energy goes down. So whenever one goes in one direction, the other one is following. They're going in the same direction. We say that they are directly related. Okay, here we're talking about all of our colors again. So this one asks which color has the highest frequency. We know the highest frequency is violet, and it makes sense for it to have the shortest wavelength because if the frequency is high, we know wavelength is inversely related, so it's got to be low. It's going to go in the opposite direction. Because if I see a whole lot of waves, I'm not going to have a whole lot of space in between each wave. Number 2, which one has the longest wavelength? Well, that's red. And it makes sense for it to have the lowest frequency because they're, again, inversely related. So if my wavelength is high, my frequency is going to be low. If I have a gigantic gap in between my waves, I'm not going to see a whole bunch. So based on the data, describe the relationship between energy and frequency. Well, we know they are directly related, that the higher the frequency, the more waves we're going to see, and the more energy we're going to get. And our Venn diagram. So we know that mechanical waves are longitudinal. Both waves can travel transverse. Mechanical waves, sound would go in mechanical waves, right? Because sound has to have a medium. Waves on a string, also mechanical, because if the string was not there, then there would be no wave. Visible light, microwave, EM waves. Travel through different media. Well, technically that's both of them, because EM waves can do that. Doesn't require it, but they can do it. Mechanical waves just require it. Travels through a vacuum, EM. Travels as a disturbance of a medium. Technically could be both, but as a disturbance of a medium, we're going to go mechanical. Because then we see travels as a disturbance of electric and magnetic fields. That's only electromagnetic.